Swayam Prabha. Digital India. Educated India.
Okay, welcome again to this video series on basic surveying. And today in this video lecture we are going to talk about again module 2 and lecture number 5. If you look at our structure of the video lectures, this is the lecture number 5, though it was our writing number 4 here. I was planning that we will have only 4 lectures, but in order to accommodate some material which is very important, I am inserting one extra lecture here. What we have done so far in last 4 lectures, particularly this last one, the 4th one, we talked about the distribution of random error. We saw what kind of distribution it follows, the normal distribution. We saw the equation also for the normal distribution. Then we looked into, because once we know our observations, once we remove the blunders and outliers from the observations, also from the observations we have removed the systematic errors. Then the observations still are not the true value. Why they are not true value? Because still there are some errors in the observations. Something which we collect from the field, still some errors are there, and those errors are the random errors. Now, random errors, as we have seen, will be always there. We do not know the sources of those random errors. Even if we know the sources, it is difficult to model them. And generally, maybe a single random error behaves to be in one direction, like the systematic error. But if all the random errors are put together, the behavior is, as we have seen in the normal distribution curve, towards the negative side equally and towards the positive side equally. The likelihood of large errors occurring is very less, and the likelihood of smaller errors, smaller random errors occurring is very more. So this is what we have seen, and we saw that the random errors are distributed like that. Okay, once we know this, what to do of that? Well, we try to make use of this, because we know it has been also observed that the observations which we take in field do always, or mostly I will say, unless there is some bias, behave in this normal distribution. So what we will do, we will start making use of this concept, this theory, because we know our observations are normally distributed, they follow a mathematical law, so we will start making use of that. Well, so this is what we saw in the use of normal distribution curve. While we are talking about this use of normal distribution curve, we talked about various things. One important thing was standard normal curve. Because in order to determine anything within the normal curve for any variable x, we cannot determine it directly. So what we need to do, we need to make use of the standard normal curve, for which we know the probability, cumulative probability density function, or that is also called distribution function. So making use of a standard normal curve, we can determine the probabilities of a variable occurring between any value, any two values, as you are seeing between x1 and x2. What is the probability that our variable x occurs between two values x1 and x2? So for this kind of answers, we can make use of the standard normal curve. Then we are looking into some indices of precision. Precision means the closeness of observations. We saw using some examples also that there may be some observations for which the spread of the observation is very big, while there are some observations in which the spread is very small. So the spread, when it is small, we say highly precise observation. Well, how to quantify it? We required a method to quantify it. So what we did, we made use of standard deviation. Because once we, from a table of data, the observations which have been taken, Once we compute the standard deviation tells us the spread of the data. That what is the deviation from mean value where 68.3% of the data do occur. If the standard deviation is large, we say the observations are less precise. If the standard deviation is small, so the deviation of observations from the mean value is less. So the observations are more precise. But just standard deviation doesn't help, because we are not talking about how many observations are there. When we want to be ensured about the confidence, we want to associate to a mean computed from a set of observations, we should also include how many observations were there. So to make use of this, we made use of standard error. Well, next we looked into the weighted observations. This is very important in the sense that the reliability of observations there in the field is not same. We saw many cases, many examples why the reliability is not same. If the reliability is not same, should we give them same treatment, same value? When we are deriving any result, we have some results from the field, we want to make a prediction, we want to plan a road using those results. Should we give same weightage to all those observations? No, answer was no. We discussed it. Then how to quantify the weights? We saw some methods. Number one, your personal judgment. You know, okay, this particular observation has got less likelihood to be more reliable. Then number of observations. If a particular quantity has been measured many times, the chances are the errors are less in that. So that is the number of the observations. So the weight is proportional to number of observations n. Then the other thing, precision. We know precision is an indicator of the accuracy, provided we eliminate systematic errors. So precision becomes an indicator of accuracy. So if the precision of the data is good, we say our observations have got higher weight, they are better. So what we did weight was inversely proportional to the variance, and variance is an indicator of the precision. Then what we saw some measures of precision also for the weighted data. So this is all what we have done so far in our last lecture. What we will do today in this extra lecture, the 5th lecture in module 2, we are going to use the standard normal curve. I will solve a little problem so that the way in which we make use of a standard normal curve becomes clear to us. Then we will talk about one very interesting area, which is the outliers in observations and how to detect the outliers by a quantitative method. Then we will see another very interesting area, which is the error propagation. So we will talk about all these things today. Okay, so today we will start with one little problem, one little numerical. The problem is, you are given, for example, for a length, a set of data. The data means this length x was measured many times, I is 1 to n, and from the observations the outliers have been eliminated as well as the systematic errors have been eliminated. So in our observations only the random errors are there and they follow the normal distribution. So the data is like 12 to square. What is the meaning of this? The meaning is the mean of the data is 12 and the standard deviation of the data is 2. Well, the answer that we have to provide, we have to find the probability that our variable x, that's our variable x will have a value which is less than equal to 10. Also, number 2, we have to find that the probability of x being more than and less than 11 and 15. Also, the third one, because the treatment in this third case will be slightly different. So this is why I am giving this third one case also. We have to find the probability that our x is more than 16. So what we have been given? We have been given a data, and the data is found to be normally distributed with these parameters. Now how to proceed in this? Definitely we will make use of the standard normal distribution. But how to proceed? Well, to proceed in this, first of all, the value x which was given to us, we will transform it into the standard variable z, and the standard variable z in this case becomes x minus x bar by sigma. So this is, we are transforming our variable, we are making it standard, and using this we can make our variable standard. We have seen this before also. Well, in the first case, the case number 1, probability is less than equal to 10 of x being less than equal to 10, we can write it as, if we convert our variable now, transform our variable. So what is this value? If you transform this value, so 10 will be equivalent to x is 10 minus x bar, as you can see here, the mean is 12 divided by sigma, which is 2. This value is 2. So we can write the equivalent value is minus 1. So what we can write this as? This probability is same as in the case of our standard curve z being less than equal to minus 1. Now what is this z being less than equal to minus 1? If I draw my standard normal curve, this is how it will be, from minus infinite to plus infinite, okay, and the value, the mean here is 0, the standard deviation is minus 1 and plus 1 here. So plus minus 1 is the standard deviation. This is what is the standard normal curve is. What we are looking for? We are looking for the probability that the z is less than equal to minus 1. So you can see here that is equal to the area shown by the shaded region. Now how we find this? This area, as we have seen, is equal to, in terms of the distribution function, z minus 1. So what is the value of the distribution function for minus 1? So that is what we need, and for that we'll need to make use of the table. So we have to find the value from the table, and here is the table. This is the table for standard normal distribution function. Now in this table, here are the values of z for which we are writing the distribution function f z. And what is the value of that? So we see along this, it starts from minus 3 here in this table, though it should start from minus infinite to plus infinite. So minus 3, it will go up to plus 3, and over here if you follow, here is the highlighted one, minus 1.0. We need a value of f minus 1.0. So what we see in the corresponding values here, the value is 0.1587. So this is the value, 0.1587 is the value of f minus 1.0. So as we have seen from the table, we are writing here now the value of the distribution function for standard normal curve for corresponding to minus 1 is 0.1587. What is the meaning of this? The meaning of this is the probability, as it comes from here, the probability that Z will have a value less than equal to minus 1, this area is this value. So, we can say again that the probability of our original variable x, the probability that x is less than equal to 10 is 0.1587. So, this is how we make use of the normal curve in order to determine the values. Now, what we will do, we will go back to the problem number 2. It was slightly different in the sense that we have to find for this x which is more than 11 and less than 15. Well, we will try to go very fast here. 11 x less than 15. What it is equivalent to? What we will do, first we will transform these values in their corresponding standard variable or standard values. How do we do that? We have seen that already, as we saw here, x minus x bar divided by sigma. So, the value of x here is 11 minus 12 by 2, and in the other case, that is 15 minus 12 by 2. So, these corresponding values are, as here, minus 0.5 and here plus 1.5. So, what we are looking for? This particular probability is same as probability that our standard normal variable, it is more than 0.5 minus, of course, minus 0.5 and less than plus 1.5. So, what we need to do? We need to find from our standard normal curve this particular value. Well, what I do? I will draw this curve for you again. Okay, that's 0 is standard normal curve, minus infinite to plus infinite, and that's the Z, our variable. Now, what we are looking for? We are looking for the area of this curve within minus 0.5, which may be somewhere here, minus 0.5 and plus 1.5, plus 1.5. So, we are interested in the shaded area. How do we find it? How do we find it? By making use of the table that we have just seen. In the table, what the values that are given to you are only f, z. Well, what we will do? In order to make use of this, we can write this as probability that this shaded area is the total area. The total area, if I mark by red dots, that is the total area, minus if I mark the area here by green dots. So, what these areas are? These areas are the area which is marked by the red dot, that Z is less than plus 1.5 minus probability that Z is less than minus 0.5. So, what we need to do? We need to now collect from our table the corresponding values, and the way we will do it is the same. We will go back to our table and we will find these answers. Well, I am not looking into the table now, I am leaving it to you to go to the table and find the answer. The answer in this case, of course, when you find the differences, will be 0.6247. So, please check your answer also, do it yourself. Well, now we will go for the third part. It is slightly different, we have to handle it in a different way. So, we should know how to handle this also. Well, the third part is we have to find the probability the x, the variable, is less than 16. I am sorry, is more than 16. That x is more than 16. Now, how do we find it? What initially we will find the corresponding value to the 16, and that will be 16 minus 12 divided by 2 as the usual case. So, 4 by 2 plus 2. So, that is the standard normal value corresponding to this 16. Well, the probability that x is more than 16, it is same as probability that our standard normal variable is more than plus 2. Now, what is the meaning of this? If you look into the standard normal curve, so I will draw the curve again for you. Well, this is the standard normal curve, minus infinite to plus infinite, this value is 0. If this is the standard deviation, it is 1 and 1. We are interested in z more than being plus 2. So, plus 2 is somewhere here. So, which area we are interested in? We are interested in finding this area. The tables, they give you the values starting from here, the way your variable increases. So, how to find it? Well, this we can write it is same as you can see here, this area is same as the total area, which is 1 minus this white area here. If I do blue lines, so shaded by blue color, so 1 minus the area which is shaded by blue color. What is that? The area which is shaded by blue color is probability that your z is less than plus 2. Okay. So, what we are looking for? We are looking for this is same as 1 minus probability that z is less than plus 2. So, we will now find from the table the value corresponding to this, and this value from the table you please determine it and find the answer. The answer for this problem should be, I am going to write this one. So, the answer for this is 0.0228. So, you try to find this answer using the table. We have seen use of the table. Okay. So, one more thing here, because we are writing here z is more than plus 2. So, we should write here less than equal to. Okay. So, that mathematically this is okay, and please find this answer. So, this gives us how we can use normal curve or the standard normal curve in order to answer the questions like this. Well, having said all this, now we will go further in our discussion. We are going to talk about a very interesting area today, which is called outlier. Now, first we will talk that why and what are outliers. You remember that old example where this is the bull's eye and our target, and you are firing in the target. So, while you are firing in the target, you are a very good fireman, you are using a very good rifle. Most of your bullets are in this area, very precise. Okay. But somehow one of the bullets is here also. Now, your firing instructor will say that you are very good in your firing. How come you fired a bullet here? the moment he looks at your target, even you yourself, the moment you look at your target, you yourself will feel, how come I could fire such a wrong? Though mostly your observations are here. So what it is? It is definitely because of some problem. Something went wrong. While you're firing, maybe you looked somewhere else, something went wrong, and this is why you have a value here. The same thing happens. For example, let us say our line. We want to measure this line, and there in the field this line is 100 meter. Well, you are taking the observations, so your observations may be 99.90 meter, 99.91 meter, 100.34 meter, 100.02 meter. Similarly, you will have many observations. If you end up with an observation which is, let us say, 19.99 meter. So what are you doing? Just by looking at your observations, you are able to say that this observation, though it is recorded in your notebook, doesn't belong to this set. Now, how this observation came into this set of the observations? Maybe you are making measurements of this length while your friend is recording the readings. Somehow he misses something, he misses writing 99.99, rather he writes 19.99. It's a kind of blunder, a mistake. So this kind of observation we say also outlier. If there are outliers in our observations, we need to reject them, we need to eliminate them, so that our observations are more purer. I will give you another example here, that how you can see the outliers. For the same length, if I plot the length here, let us say along this ordinate we have the values and 100 meter is around here. Well, the values which you are taking, and these are the observations, the observation number 1, 2, 3, 4 and so on up to n. So these observations will be plotted something like this. Because they will be around the value of 100, the true value of 100, they will be here and there of that value. So this is actually the spread of the point we have seen is the precision. Now let us say one of your observation is lying here, then you suspect, no, it cannot belong to this set of the observations. So obviously this is going to be the outlier. Now the question is how to find outliers, how to determine them, how to locate them. Well, the method number 1 could be your personal judgment. As in the previous case, looking at these observations, you can straight away, right away, you can delete this set of this observation. No, it can't belong to my set of observations. It has to be an outlier. So this is the personal judgment which you are doing. Many times the method number 2 could be the physical constraints. Let us say you are measuring the height of a building. Okay, you are measuring the height of the building, and the height of the building, it cannot be more than a certain value in no case. So if a height is measured like that, so most of the heights which are measured will be here and there of the actual height. But if there is a value which is physically not possible, physically there is no building in the town which are more than this height, you can easily eliminate those observations. Physically it is not possible to have those values. Well, the method number 3, because these first two methods are based on your intuition. Our intuition is really not very helpful, because we are trying to make some subjective judgments about the observations. So the third method, it says you reject an observation provided it deviates from mean by plus minus 3.29 sigma. Now we will explain the meaning of this. What is the meaning of this, what I am writing here? What do we mean and why it is so? We will try to explain this. Why 3.29 sigma? Well, if you look at the normal distribution curve, the normal distribution curve is like this, where this is the mean and we will have the standard deviation somewhere here, okay, minus sigma and plus sigma. Now, this 3.29 sigma plus minus, this corresponds to 99.9% of area of this standard normal curve. What is the meaning of this? The meaning is, if I draw it with a different color here, this entire shaded part of the curve will have 99.9% of the data. Now, the rest of the data, 100 minus 99.9, this data will stay outside here, because this is now a very feeble possibility, this percentage. The occurrence of the data which is here is a less probability. So what this rule says, if your data deviates from the mean by more than 3.29 sigma, that is, it has a probability, very small probability, which is this value only, then reject it. So from a set of observations, if these are the observations, what we do, we find the mean, we find the sigma, and we find if at all there are any data which are more than, which deviates more than this value, we outrightly reject them. Okay. Now, there is one disadvantage of this method. What is the disadvantage? The disadvantage is we are not considering number of observations. There may be 10 observations in a set of data, there are 1000 observations in a set of data, there are, for example, 10,000 observations in a set of data, and our treatment is same in all the cases. This is wrong. We should not do it. Now I will explain why. For example, let us say n is equal to infinite. Now for n is equal to infinite, in our normal curve, because n is equal to infinite means we have got infinite observations. So even if the values are here, even if this value, this value, this value, however small the probability is, it will occur. It will definitely occur when we are taking the observations. Also on this side, however small the probability of these values are, but they will occur because they are infinite number of observations. So if the infinite number of observations are there, we cannot reject these values, because these values will occur however big they are. Now if n is very small, what happens if the n is small? If n is small, as we know in our normal distribution curve, also the way our random errors behave, we know it that the probability of occurrence of values which are nearer to the mean is higher than those values which are on these sides. We know it. This is how the random errors behave. So, if our n is small, we are more sure about the values which are on somewhere in the middle part than on these parts. So, there is a rule, and that rule is based on number of observations, and which is based on the concept what we have just discussed. What that rule is? The rule is you reject an observation, because what do we have? We have a set of observations. Okay, we may have 10, 100, as many as number of the values. We have a set of observations. We want to reject some of these because we say they are the outliers. How do we say that they are the outliers? So, the rule in this case is reject an observation provided its probability of occurrence is less than 1 by 2n. I will explain it. It says reject if probability of occurrence is less than 1 by 2n. Now, what is the meaning of this? We will try to see this in again the normal curve. I am drawing the normal curve again. This is important, and we must understand this what we are doing from minus infinite to plus infinite, and that is the mean. Okay. Let us say 1 by 2n is a value x r. The value of the variable x r is the value of the variable. It is x r. Now, we are saying you have to reject an observation if its probability of occurrence is less than this. So, whatever we are computing 1 by 2n, let us say 1 by 2n is this. Now, if you find 1 minus x r, what it will be? What I am doing, this side is an area which is x r by 2. Do not confuse by x r as the variable at the moment. This is an area x r by 2, and here is also the area x r by 2, while the area in between which is shaded is corresponding to this. Now, what we are saying? We are saying we will try to reject those values which have a probability of occurrence which is less than x r by 2. If I write it the other way around, it means we are looking for the variable x, so that probability of occurrence is less than x r by 2. All those variables, all those values we will remove. Okay. So, the same thing will be on the other side also here. Well, what we will do? We will try to do it by an example. Let us say n in our case is 10. So, 1 by 2 into n, 1 by 2n, that is corresponding to 0.05. Now, what we are looking for? Again, I will go back to our curve. We are going to reject observations which are on the tails of the curve and having a probability of occurrence, all those variables having probability of occurrence less than this value. Okay. So, now in this case, what is the meaning of this and why we are doing it actually? We are doing it because the area in between here, which is 1 minus 0.05, we assume all these values are closest to the mean. Obviously, this is the area which is closest to the mean, and the areas which are on the tails, we want to reject it as per our rule. So, in order to reject it, how do we find this value? Again, we will make use of the normal curve. So, in this case, what we will do, we will look in the normal curve. If I write here for f, let us say the variable here is x. So, we are looking for a value fxi for which the value is minus 0.025 corresponding to this value here. So, what is the meaning? All those variables, because what does it say? We have seen this before also. All those variables for which the probability of occurrence is less than this value here. We want to know this value actually. The idea is we want to determine this value, what this value is. Okay, that is what our concern is, because in order to reject the observation, we want to know what this value is and as well as what this value is. If I know this value in terms of my sigma, so I know this deviates from my mean by this much, and I will reject all those values which are larger than this and here which are smaller than this. So, I am interested in knowing this particular value and this particular value here. And our rule says that below this value, the probability of occurrence of all the variables should be this. Okay. Why I am doing half? Because half is on this side and half is on this side. Our outliers could be on negative side, could be on the positive side. Now, the corresponding value for this xi, if you go back to our table, you can make use of the standard normal curve table, and this value is 1.96. Over here it is minus 1.96 and over here it is plus 1.96. So, what does our rule say? Now, if n is equal to 10, as in this case, our rule says from our set of observations, reject all those observations which have variation. If I am writing mean by this, plus minus 1.96 sigma. So, in our standard, in our normal curve, in a normal curve, that is our mean corresponding to 10 observations. The rejection criteria is this. So, that means remove the observations which are beyond 1.96 sigma. So, how to attack this problem? If you have got the data, you have this data, how to answer this question? Well, first of all, you find the mean of the data. Let us say I am writing the mean again as mu. So, we can find the mean, no problem about that. Also, we can find the sigma. You know how to find the standard deviation. Then, how many observations are there? You know it, the value of n. Once you know the value of the n, you find 1 by 2n. Again, whatever is the 1 by 2n, half of that, because it is on this side as well as on this side. So, that is the value of our fxi, and corresponding to this value, we want to determine the value of xi from the standard normal table. And once we have found the values, as in this case we found the value to be 1.96 minus here plus here. So in your set of observations now, you can find 1.96 sigma, whatever it is, you know it. So start looking, are there any values which are less than this value, mu minus 1.96 sigma, or more than mu plus 1.96 sigma? If it is so, reject them. The only thing is, we do this exercise only once, not in iteration. Just only once we do it, we reject the observations, and that's it. Okay, having discussed this, the last part of it, that is about error propagation. Also this is said combination of error. Now what happens many times? You are taking the measurement, let us say one length, another length, another length, another length, L1, L2, L3 and L4. Your job was to find this full length. So what you do, you find this full length by sum of these individual lengths. So what you did, there in the field it was not possible to measure the entire length in one go. So what you did, you measured the lengths in parts, and in each of these there was sigma 1, sigma 2, sigma 3 and sigma 4 kind of errors. What we are interested in when we are talking finally, we are interested in what will be the error in L, while we know the standard deviations of these individual ones, or what is the variance of this final computed value. Another example, you have a field, you find these angles as well as these lengths. All these are measured. While you are measuring any length, you also know the corresponding standard deviation, or we can say the variance. Similarly, for all the angles also, you know the value of the angles, as well as for that angle which you have measured, what is the standard deviation. Now, the area of this land parcel is a function of L and theta. In L and theta, for all these lengths and for all these angles, we know their individual standard deviations. What we are interested in? We are interested in the area which we are finding, how confident we are about that area. Because what is the standard deviation? Standard deviation is a kind of measure of confidence, confidence in our result, the precision. So we are interested here how confident we are about this A. For that, we should know the standard deviation of A. So very simple rule is there, and this rule says for any function, if I write it now in a general form, y is f x I, where I varies from 1 to n. The meaning is we are using n number of variables in order to arrive at y through some manipulation of these variables, and for each variable we know its corresponding standard deviation. So in that case, the standard deviation of our final output y, I am not going into the derivation of this because this is beyond the scope of these video lectures, but you can see in any good book the derivation also. So this is given by, as we write here, sigma partial derivative of f with xi multiplied by the standard deviation of that, if you are writing at xi here, of that variable, and square of these, and here also it is square. So this is how it is given. So what you can do now, you can make use of this and compute the standard deviation of your final value. So we will do a little example over here and we will see something very interesting out of that example when we make use of this. The example is, let us say there is a length C, and this length was measured in two parts, A and B. Okay, this is what we do very often in surveying. We have to do it. Many times you will measure the individual things and then you finally come out with the answer. The simple example is, area, or maybe any complex example. You want to measure the tilt of a tower. The tilt of the tower will not be given to you directly by any instrument. Rather, what you will do, you will take couple of measurements. Maybe you are measuring some angles, some lengths, there on the ground, in the vertical, and all these values, all these measurements which you have taken, they will pass through a trigonometric relationship. And once they pass through that trigonometrical relationship, you will find your answer, the tilt of the tower. But we want to be sure about that tilt of the tower, that the answer that we have given, how confident we are about that. What is the precision of that answer? What is the standard deviation there? So this is a very common problem, and we should always, whenever we are computing, whenever we are doing any kind of computation, we should know doing this thing. For our formulation for this tilt of tower, we should know how to arrive at the standard deviation of the final value. We should be able to compute that. But a little example here. This example is, we want to measure C. We want to determine the length between point here number 1 and point 2, which we did by measuring A and B. So the length will be straight away written as A plus B. So a length is given to you, but that's not enough. A had a standard deviation of sigma A, similarly B had a standard deviation of sigma B. How do we know these standard deviations? For example, this B was measured, let us say, 10 number of times. You have 10 observations for B. You can compute mean, you can compute the standard deviation. Similarly for A. Well, we know the length, but we do not know what is the confidence yet. So what we try to do, we try to find sigma C, which we have seen as will be now partial derivative of C with A into square of this standard deviation of A square plus partial derivative of C with B into sigma B. Now if you compute this value, sigma C square, now standard deviation of the C with A will be 1, so that becomes sigma A square. Similarly here, sigma B square. Well, so by that we can write, we will write in the next slide, sigma C is under root of sigma A square plus sigma B square. Okay, the answer is there. Of course, we must write this plus minus. One more important thing. We saw here in the previous case that the sum C is A plus B. Let us say we have a different thing. The different thing is, we are interested in finding our C, which is this length, while the thing that we measure is A, the full length, and as well as we measure B here. That is also possible. We can arrive at C. So C becomes in this case A minus B. Now can you think of what will happen to sigma C? Actually, if you do the derivation, you will find sigma C will again come out to be sigma A square plus sigma B square. You must do it. Now what do we observe from this? In both the cases, whether there is a sum like this, A plus B or A minus B, our value of this standard deviation for final output is same. Obviously, Because what is happening? There is some error which is being introduced by A variable, some error being introduced by B variable. It doesn't matter whether these variables are subtracting or adding. It doesn't matter, because our errors are being added, our errors are accumulating. So final error will be more. That is why in both the cases it is so. So what you can do, you can solve many more numericals, many more examples on this line. I'm not solving the examples here because the time is the limitation, but you can make use of your books, all the books which we have referred to. I have given you many books. Go through those books, you will find many examples and solve them. That will give you a confidence in order to arrive at the answers. So what we have seen so far today, and as well as in this module 5, because we are going to end the module 5 today. We started with what the surveying is, the basic surveying. We saw many examples. Then we saw about the the scaling thing, the plotting accuracy, many principles, whole to part, reconnaissance. We have seen all those things. Then we talked about the measurement, the basic thing. It will be affected by the error. We must start treating the error. Outliers, well, we have seen we can reject them. Systematic error, we'll see it later on also. If you have any systematic error, you know the physical rule behind it, you can eliminate that also. Now the errors which cannot be eliminated are the random errors, but we have to still treat for them. We should know what kind of observations are there with us. So whenever we are writing an observation or a measurement, we are reporting it, we should report it as L plus minus something of sigma. This is how we are communicating our measurement with the kind of the confidence which is there with the observation. So all these things, these basic concepts of surveying are very, very important. Henceforth, we will start talking about the instruments, the measurements, but we must keep all these things in our mind. So we will finish our video today at this point. Thank you very much.